I'd like to first start off by saying I really appreciate being involved with CAPSULaser, and thank you, David, for involving me. It's been a fun journey for a few years now, it's been absolutely fantastic. And we need to congratulate David today. We've just announced that it has got CE marking, so why don't we give him a round of applause. Anyway, my talk it is a basic science talk. It's a laboratory study that was not performed by myself. I happened to write the papers and work with David in terms of putting it together. The data was put together by David, and I sort of presented in this sort of format. I'd like to acknowledge the workers in Singapore. This is a talk that actually I'm going to be giving at the ESCRS with Professor Chi was involved in saying these in the audience here somewhere, who did a lot of the actual procedures as well. And Richard Packard has also been an advisory in this area. So I have a financial disclosure. I'm also an equity holder of Excellence, the CAPSULaser. So Burkhardt already elegantly described the variety of techniques available for performing an automated capsulotomy. Capsulorhexis was definitely a big thing 30 years ago. I did my first phaco in 1989, and I was instructed to do a capsulorhexis at the time by David Payton, my old chairman. This is in the United States. And yes, I used tomatoes to do it, and I did okay. But there's no question using Femtosecond laser and using some of the devices makes things easier. But how do we make it more affordable? And I think David has come up with a solution for that. One of the issues with capsulotomies is capsule strength. And looking through the literature, anterior capsular tears, and also my own experience, anterior capsular tears can be really hazardous. They can extend out. You can get the Argentinian flag sign and white cataracts. But even in tags that occur or tears that occur during surgery, if you're not careful, you don't bring down the bottle, you could wind up getting a posterior extension, and then it's all over in terms of getting a good refractive outcome. The patients require a lot more interventions, and they could land up with horrific complications like retinal detachments and so on. So one of the studies that was done in Singapore was a laboratory study looking at the influence of capsule size and the continuity of a capsulorhexis. So they're divided basically into two groups, ones that were between 4.7 millimeters to 5 millimeters. These are all done by capsulorhexis, and 5.2 to 5.7 millimeters. And also capsule continuity, and this diagram down below tries to represent that. This is a discontinuity, and you've seen that, when you've done capsulorhexis. Sometimes you have a little triangle or sort of heart-shaped capsulorhexis. Well, we want to find out if that influenced capsule strength. And the answer is in this slide. So I'm not going to bore you with all the details, but what was looked at was the distension perimeter. How far did the capsule stretch with these little devices that were used to stretch the capsule, and what load was required to actually break the capsule. And you'll see there's statistically significant. The discontinuous did badly, and smaller capsules did worse than bigger capsules. So in a nutshell, this is the discontinuous versus continuous, and this is capsule size. So capsule size, the bigger capsules did better. And there's been some evidence to support this. Rafael Barraquer did some studies on human eyes showing that the capsule is thicker at about the 5.25 to 5.5 millimeter zone compared to 5 millimeters. So again, in summarize that particular study, discontinuous capsules are weaker, and so don't do them. And capsule size, well, bigger is better, but not too big. If you go beyond 6, then the capsule gets thinner again, and it could be a lot weaker. So the second study that was performed was to compare femtosecond laser capsulotomy with capsulorhexis and also selective capsulotomy. And this was done by using a paired human cadaver eyes. So what we do is we divided into 3 groups. We got paired cadaver eyes, and they were divided into selective laser capsulotomy, which is CAPSULaser, compared to capsulorhexis. So one eye had one procedure done, and the fellow eye from the same donor had the other procedure done. And then there were another 10 eyes where capsulorhexis was compared to femtosecond, and then a third group where femtosecond was compared to CAPSULaser. And we also looked at these edges using a scanning electron microscopy. So all eyes, the cornea and the iris was removed for visibility, and they were excluded if the circularity was poor. So if they were discontinuous in capsulorhexis, they were discarded, and other eyes were used to perform the procedure within the range. And the circularity indices used were the ones described. The ones you probably easiest to understand is the minor axis versus major axis. If there was a more than 90% difference, that eye was excluded. And size, if the diameter was outside 5 millimeters plus or minus 0.2, they were also excluded. And this is the surgical method that was used also for the first study, where the lens nucleus was expressed, IA was done with the cortex, and then a wax probe was inserted into the bag. The zonules were cut and the bag was removed. This is all described by Liliana Werner and Nick Mamalis and his group in Utah. And then there's an Instron device that moves at a small pulse, I think it's 0.15 or 0.1 millimeters per pulse, stretches the capsule and measures the load, and the perimeter is also measured to see how far it goes before it tears. And the statistical analysis that was used was Wilcoxon signed rank tests. So what did we find? Well, if you take a look, what's interesting was the amount, the perimeter for selective laser capsulotomy was remarkably similar in the two different study groups, although there were different eyes used. And the same can be said for capsulorhexis in red. You can see that right here. The perimeter was similar, as was the load. And the same with femtosecond laser. So this actually was a good study, because you got consistency of load and perimeter in spite of being in different groups using different sets of eyes. So this makes it a strong study. So what were the results? So looking at group 1, which compared CAPSULaser to capsulorhexis. Looking at perimeter, the P value was 0.01, indicating that there was a statistically significant difference between CAPSULaser was stronger than capsulorhexis for perimeter and also load. If you look at the second group, capsulorhexis versus femtosecond, so the femtosecond users in the audience, including myself, might not want to hear this. For perimeter, it didn't make much of a difference, but for load, there was a higher load, significantly higher load required to break a capsulorhexis than a femtosecond laser capsulotomy, with a P value of less than 0.01. And when we compared a CAPSULaser to femtosecond, well, it followed that this was significantly better than femtosecond. CAPSULaser was better than femtosecond, again, with p-values of less than 0.01. So in summarizing this, so if you took capsulorhexis and made that 100%, relative to that, CAPSULaser required was 120% more stretch with a standard deviation of 10%, and the load was considerably higher at 146% increased load compared to capsulorhexis. And if you looked at capsulorhexis versus femtosecond, again, femtosecond was weaker. As I said, this is the yardstick 100%, 95% for perimeter distension, and 78% of load. So femtosecond laser capsules broke much more easily. If you look at scanning electron microscopy, many of you have seen this in the journals, a nice smooth surface for capsulorhexis with a lamellar structure that's visible. And if you look at femtosecond laser, this looks like a bit of a mess. You've got these pulsatile areas here and also aberrant holes. Now you can imagine this could be weaker because you've got a whole bunch of fault lines within the capsule edge. And looking at CAPSULaser, this is the anterior capsule here, and it's got a rolled over edge. Looking in with more magnification, this is the edge right here. And you've got amorphous collagen, which is denatured collagen from the heat, which provides increased elasticity. So the strength of CAPSULaser capsulotomies could be accounted for by looking at those scanning EMs. There's a doubling of the capsule edge. It's rolled onto itself, so you've got a double capsule on the edge. You've also got it's also folded, which if you take a piece of paper, you fold it and try tearing it, it's harder to do. And the smooth area, there's no fault lines that could extend out and break. And you've also got thermal change of the anterior capsule that provides a little bit more elasticity as well. So the 4 reasons there for why CAPSULaser capsulotomies are stronger than both CAPSULaser and also Femtosecond. So this is a strong study because we used human eyes. If you look at the literature, they're all porcine eyes. And they're different. They have different elastic properties, and there are also different areas of thickening within the anterior capsule. And the variables were standardized. We standardized in terms of size and circularity, and we had consistent load and perimeter findings between the groups for each type of capsulotomy performed. So CAPSULaser is stronger than CAPSULaser, and the CAPSULaser is stronger than Femtosecond. Thank you for your attention.